Wait, setting up. In a couple of seconds, we shall be live on YouTube. Perfect. Great, Jean, you're ready to go.
Okay, thanks. Good morning. I'm Jean Goubeau-Larec, and I'm going to chair this session where I'm incredibly happy to welcome Professor Sophia Drossopoulou from Imperial College London. Sophia Drossopoulou grew up in Greece and finished school in Athens, studied computer science at the Technische Universität Karlsruhe, where she obtained her PhD and a lecturer position. And then she moved to Imperial College, where she worked as a research associate, then became a lecturer and so on. And now she's a professor of programming languages. She did too many things for me to mention in any reasonable amount of time. She worked on in an incredible amount of aspects of programming languages. She worked on the first Ada compiler. She worked on the first semantics of Java. She proposed the idea of idea reclassification, which evolved into something called type state. She has co-developed the first robust ownership types model. She has collaborated on the first introduction of session types into object-oriented languages. She has proposed evolution from object-based dynamically typed to class-based strongly typed disciplines, which then became gradual typing, and hence and then more recently, she contributed to the Pony programming language. And recently, she has been working on what gives the title to the presentation, meaning holistic specifications, and on the semantics of and the design of the programming language Verona, developed by Microsoft Research. Sophia?
Thank you very much. I am very excited to be talking about this work. And thank you all for coming. It is a work that spans between the needs, I believe, that we have in programming languages and formal foundations that need to be discovered. So here are the collaborators of this work. I'm sorry. We have obtained money from various sources to do it, from 3 companies and the New Zealand Marston grants, and we have also had quite a bit of volunteer time. I think that is the case for all our research, of course. So how did that all start? It started several years ago when Mark Miller was discussing with James Noble. Mark Miller has been working a lot on capability-oriented programming and how to make JavaScript safe. So he has been discussing with James Noble about new encapsulation features that are needed and new ways to talk about privacy, constant values, things that do not change, things that cannot be read, and how programming languages can support those features. And James Noble, he's the developer or one of the main forces behind ownership types, which are type systems that give you a more sophisticated notion of encapsulation, that tell you what can be accessed from where, what pointers exist from where. So there was this discussion and I was listening, but then I asked, what should the guarantees be for these features? Before you decide what features you want and how they work, we need to know why we want them, how they will be used. And James put it very succinctly. He said the encapsulation features, they are mechanisms that allow us to write robust code, but we do not yet have a way of describing what is robust code. So this is what I'm going to be arguing today. I'm going to argue that the traditional specifications, they do not adequately address the issues of robustness. I'm going to give you an example of what the holistic specifications are, how robustness can be addressed, the semantics, and I'm going to, if I have time, I'm going to talk about a particular part that is trust and obeys. So the first argument, in a traditional specification, you have a closed world view. You know all the code and you want to prove that this particular code has got some properties. Whereas if we want to talk about robustness, we worry about the open world. We don't know which code we are calling. We are calling into another web page, and we still need to protect ourselves from the things that it can do to us. In the traditional specifications, we are talking about sufficient conditions for something to happen. Namely, for example, if my account has got enough money and I pass my credentials, then I can make a payment. But for robustness, we are interested at the other side, for necessary conditions. For instance, I want to know that no money will leave my account unless I have given the permit for that. So it's about a necessary condition for the money to leave. In the traditional specification, we talk about individual actions, whereas in robustness, we talk about the emergent behavior, about everything together. So that is what the traditional specification looks like, I would say. And I'm going to now show an example. So we have a class safe, and it has got a secret and a treasure. These are fields in the safe, and it has got a method that allows me to take the treasure out of the safe. So for instance, here what I do is I check if I have passed in the secret of the safe, then I will return the treasure, and the treasure in the safe will be overwritten by null. And I have got a constructor that allows me to create a new safe. So that looks like a good code. And the specification, this is the traditional specification. It says in terms of a Hoare triple, if true holds, and I call the function safe, the function take on the safe, then if the argument was the secret, then the treasure has become null, and otherwise it is the same as it was before. It has not been affected. So that's okay. And this first safe satisfies the specification. Now let's look at a further version of the class safe. I'm calling it safe 2. It is identical with the previous one, but it has got this method that allows me to overwrite the secret. And with this method, I have broken the guarantee. There was no guarantee. I have made the safe class not robust, because I can change the secret to something I like, and then I can take the treasure out. But the problem is that this safe 2 satisfies my specification. So I am in the quest for writing specifications that would allow me to distill what does it mean for a safe to be robust. And it should forbid the safe 2. So I can go and write another specification and say, you cannot change the secret. So specification B says, for all safe, if the secret has got a certain value, it will have it afterwards. Or we can say the secret is constant. This has also been proposed in specification languages. And then safe2 doesn't satisfy that specification, so perhaps this is a good enough specification to address robustness. But here is a third version. So what I did, I removed the bad method set, and I added a new method set, which allows me to modify the secret, provided I already knew it. So if I give the old secret, then I can change the secret to what I want. And the problem is that safe 3 does not satisfy the specification B. So I have not yet addressed, with these classical means, I have not yet addressed the quest for robustness. So those two specifications, specification A and specification B, are traditional and they do not express robustness. So I'm going again to revisit what is happening with specifications. So in the traditional specifications, we have got a space of states, and these black dots are states, and the ones that are here are the possible initial states. And then my specification gives sufficient conditions for transitions to happen between states. So the specification for function 1 introduces some arrows, some transitions into the state. And for function 2, there are more transitions, and for function 3, some more, and for function 4, some more. And now, if I have this picture, I know what are the possible transitions overall. So these kind of specifications are very precise and elegant and well understood, and very well developed, and they are being used in industry. So it's wonderful news. However, if you want to understand the emergent behavior, it becomes difficult because you need to follow all these arrows of the different colors. So if what you are interested in is the emergent behavior, it is not that good. How many specifications do I need to read in order to understand whether I have got the guarantees that I want? If I have got a data structure with 20 functions, it becomes pretty large. And if I then want to go and extend the module, which functions may I add? May I add a further function, or will it change? Will it make my module not robust? So to address this, what we want is this holistic specification. So in particular here in the SAFE, I argue that what we want to assert is that unless you know the password, you cannot take the treasure. How many functions will you use? So this is what I call holistic specification. And the holistic specification, I'm going to discuss those a bit in more detail later. Here it says, if ever in the future, the value of the treasure changes, then currently, at the current moment of execution, there exists some objects which is external to the safe, and this object has access to the secret. And this is the holistic specification, and it fits the bill. It is not satisfied by the bad safe, but it is satisfied by the good safe, safe 1 and safe 3, and not satisfied by the bad safe, safe 2. So what the holistic specification does is, what I am trying to describe here with this yellow arrow is that certain transitions are impossible. No matter how, there will be no route that will allow you to go from there to there, and certain set of states are impossible. So rather than talk about what may happen, it talks about what is guaranteed not to happen. And when you put the two together, then you have got a better view of things. The holistic specification makes guarantees about things that you are certain will not happen, and therefore you can stop worrying about them. And the other specifications, the traditional, will talk about the routes that can be taken and how you can use the data structure. So, as I said earlier, the robustness considerations are about the emergent behavior. And what we can do is describe emergent behaviors, or what we want to do is that will not happen, or instead you can say we are describing necessary conditions for emergent behaviors to happen. So I'm going to go back here. what we have here is an emergent behavior. It is through the combination of various function call, we might reach a point where we're able to take the treasure out of the safe. And for this emergent behavior, this is the necessary condition. It needs to be the case now that something external has access to the secret of the safe. Okay, so I want to give a couple of examples now. But first I will give you a summary of what you can express in holistic specifications. So we assume that there is a language of expressions that allows me to talk about this, which is the current receiver, or a special parameter with special meaning in object-oriented programming, a variable X, reading a field out of an expression, and so on. And then there are assertions that talk to the standard things, like saying some expression is larger than some other expressions, or they're equal. And then we have got the usual logical connectives. But then come more interesting things. The assertion access says that some expression has got knowledge, can get the value of some other expressions. Changes that the value of some term, like the treasure in the safe, will change. About the time, something will happen in the future, was in the past, will happen in the immediate future, past, or in the immediate future. Something holds within a certain set of objects that we use just so the objects in the set S in order to obtain an effect, and that something is external. That a function call, sorry, an object calls a function on another object with arguments, and that something X obeys a specification. So those have been in very much, these extra assertions have been very much inspired by the examples that we found in the literature where there was discussion of robustness, and they coincide pretty well with with terms that have been used by Mark Miller, who I mentioned earlier, who has been looking at capabilities and introducing the concept of capability-oriented programming. So in terms of Mark's work, if you are aware of it, of course, access is about permission. An object is allowed to read another object. Changes is about authority. Somebody has got the authority to change something. We have got time. We have got space, about something happened within a certain space, control, and trust, which is something I'll discuss later. So the examples, I will go through a couple of those examples because I want to discuss also the foundations. So the first example I am taking from the literature of blockchain. There is a very famous contract which is called ERC20, and it allows you to create your own internal currency called coin. So the clients of this can buy and transfer tokens, and they can designate others to transfer on their behalf. And in particular, a client can call the function transfer, approve, and transfer from. So transfer some tokens to another client. Approve authorizes a client to transfer some of their token to anybody they like on their behalf. And transfer from is the function that the authorized person will call in order to transfer the tokens. And the ERC20 keeps a balance, the number of the tokens they own. And using classical specifications, which first were introduced by Tony Hoare, we have triples where we have preconditions and postconditions. The postcondition essentially describe the effect. So again, I would say that the thing of the left-hand side is the sufficient condition for the thing on the right-hand side. And if we look at the classical specification for transfer, what we need to say is if I have an ERC20 and the two clients are not the same and the balance for client one is greater than something, then afterwards the client says the transfer will have happened. And the left hand, the thing at the top is the sufficient condition, and at the bottom is the effect. And what if the transfer, the balance is not enough? That can also be specified. But what about the other function? So there are more functions. There is the transfer from, two specifications for each of them, for approving, for obtaining the balance, for obtaining the total supply, for obtaining who is allowed what. So there is a lot of functions, and for all of them we have got the sufficient conditions. And if I want to ask myself whether it's robust, whether the guarantee that I'm interested in, I need to look at everything together. So if, for instance, I had added a function that takes 0.5% from each account, I would not be happy, but I would need to read all the specifications for that. And lots of questions to that effect. Instead, we want to talk about invariants, but with a slight twist. And here again, I'm mentioning that the concept of invariant was first introduced again by Tony Hoare, both for imperative code and for monitors. And then Bertrand Meyer adopted it for object-oriented programming, and it has been, it appears, of course, in protocols and all sorts of other considerations. So for our invariants, we have got state, and as I said before, time, space, control, permission, authority. So what would I want to give in the holistic specification when I'm talking about the ERC20? I would like to say my balance decreases only if the client or somebody authorized made a payment. So what I will say is there is an invariant, and it says the balance will be less than it was earlier if there exists a client, and this client called transfer, or another client was authorized on the account and he called transfer from. And now I have got the guarantee that the money will not disappear from my account. So the effect again is that the balance changed, and the necessary condition is what happened earlier, that there was a call either of transfer or transfer from an authorized client. So what does it mean to be authorized? Because I talked about authorized, I can give a holistic specification. Somebody is authorized if they previously called, if the client gave them the approval, so they called that they called the function to approve, or they were authorized for some amount, and then they transferred the amount, and then they are authorized for less money. I will now skip a couple of slides to get to another example. So this example we have taken from other people working on these issues, and it's the group with Dominique de Vries, and their solution does not involve specification as such, but gives a way of of reasoning nevertheless. I can discuss it later on. So here is the DOM. We have got a tree of nodes, and every node has got a property, and I indicate the property here through, so each of those blobs is a node, and each one has got a property. And access to any node gives access to the complete tree. So that's a dangerous situation. If you have the DOM, you want to give access to subtrees, but not to the complete tree. So how can we do it? If I have got, for instance, if I have got this unknown one, they have got access to they have direct access to this node, but indirect access to all the nodes, because also the nodes keep pointers to their children. So that means that unknown one has got, can modify, can affect all the nodes in the blue area. What can we do? We introduce wrappers rather than give the create the unknown, give to the unknown the pointer to this node. Here we create a wrapper, and the wrapper has got only limited, gives only limited access to whoever has got it. So I have created here a wrapper that has a weight 1. That means that whoever uses the wrapper can modify those nodes, but cannot modify any further. So the wrapper attenuates the capabilities of the node. It's kind of a gatekeeper. And the unknown 2, therefore, can only modify the green subpart of the tree. So let's take the example here. I've got a function that has got an unknown argument. It creates a sequence of nodes. It assigns properties to each of the nodes. Then it creates a wrapper for node 4 and gives it the wrapper weight 1. And then it calls an untrusted function on unnode with the argument this wrapper. So at this point, I know that after I called untrusted, the contents of the property for node 3 and node 2 is unknown. But sorry, I know that the contents of node 3 property is unknown, but for node 2, which is outside this green triangle, I know that its property will be stay unmodified. It will still say robust. And the question is, how can I make this argument? So in order to make the argument, I need to specify what guarantee the wrapper is giving me. And here's an example of the open world. I have got a function. I am the person who wrote the function MM. I want to give to untrusted some of my nodes, but not all of my nodes. And therefore, I give him the wrapper. I don't trust the unknown. I don't trust the function untrusted. But I still can talk with it because I have put a wrapper in between, and therefore I know that some of the guarantees that I'm interested in will be satisfied. So what I need to say in the specification of the wrapper is the wrapper allows modification of the nodes that are under this height, but nothing else. And how can I describe that? The way I describe it is to say if a node is outside a certain set, then any execution that involves no more than that set does not modify the property of the node. So, and I then need to also define what it means to be outside a set. The first specification says if the node is outside that set, some set S, that is any set essentially, then I know that if I constrain my execution with objects from that set, no, there will never be a change to the property of that node. And then I have to define what outside means. Yeah, so if the node is outside, then any execution that involves no more than the things in S will not change the property. And what does it mean to be outside? It means that if you follow the path and you to that node, if there is a path from if there is a path from anything in the set to that node, then the length is going to be bigger than the height of the wrapper. So in the particular case, we can see that the red node is outside the yellow set. And now with this specification, we can show that even though we make a call to an unknown object, at this point, the value of the property in N2 has not been modified. So there are a couple more examples that I would like to mention. One comes from the work by Mark Miller et al. In financial cryptography, where he is proposing various policies for banks and accounts. And when he wrote that, he was not particularly interested in how we specify those policies. He was interested in what are the properties that we would like to have when we have software for payments. He had foreseen the rush for cryptocurrencies. He had not foreseen it. He had written some work. He was working on things that were related to cryptocurrencies. Anyway, he had various policies, and he then used those policies to drive his design of the programming language E. The interesting thing is when we, James and I, studied that work, we realized that the first policy is classical and all the others are about robustness. So policy 2 says only if you have got access to the bank, you can violate conservation of that currency. So you cannot print money unless you can get to the bank and ask it to do it for you. The bank can only inflate the currency. You cannot deflate. You cannot affect the balance of an account unless you have it, unless you have access to it, unless you can read it, and so on. Again, no one can affect the balance of an account they do not have. The way that we can specify it is if something is an account and in the future the balance of the account changes, then there is something external to the bank and the account, and this external has access. So unless you are in a state where you can read, you have got a pointer to the account, the balance will not change. I'm going to skip a couple of slides again in order to get to the foundations. So I want to discuss the semantics of holistic specifications. And we start with a pretty classical standard object-oriented language. What is interesting is we have got ghost functions that allow us to to describe functions that look up things for us, no matter how the things are being represented in the class itself. And in order to give meaning to the holistic assertions, we have modules, which are pointers to which are mappings from identifiers to definitions, whether class definition, predicate definition, or function definitions, configurations that are heap and stack and code, and execution. And all these are defined in a pretty standard way. We define concatenation of modules in a standard way, which means if their domains are disjoint, then we make the union of the mappings. And now, what is the meaning for these assertions? I remind you again that we have got these lilac assertions that are not that standard. We define lookup as expected. For instance, here, unknown one node parent property will give me 888. And now let's look at the unconventional part. What does it mean for something to have access to something else? Well, either their meaning, their interpretation is the same, or the first one has got a field whose interpretation is the same as the second one, or the first one is the current receiver, the currently executing function, and some of the arguments of that function, one of the formal parameters, is has the same interpretation as the second one. What does it mean for something to change? If its interpretation now in the next step is different, what does it mean for something to happen in the future if there is some execution where this will happen in the future? What does it mean for something to be the case in a set of objects S? This is if we restrict the state to only have the set of object S and A holds, where restriction of the state means you take all the objects that are you restrict on the domain of the heap to be the objects in that set. Okay, so here there are some subtleties, but I don't want to go through them. I still have not said what the meaning of these invariants is, and in order to give meaning to these invariants, I need two concepts, the concept of initial and of arising. So the initial configuration is the empty configuration. There is nothing in the heap except for one object, and the stack has got a variable this that points to that single object, and that's it. And the initial configurations is those configurations where starting from an initial configuration and executing the code from that module, we reach that configuration. So arising expresses defensiveness in some way. For instance, consider this a module that talks about trees. This would be, and these two configurations. So usually trees are defined so that the top node points to itself as a parent, but there never are cycles. And you can, you know that the blue configuration will arise from the module tree combined with any other module, and the brown one will not arise for any other module with a module tree. So this module tree has got an invariant that is described here.
Sophia?
Yeah?
You've got 10 minutes left.
Thank you very much. So giving semantics to assertions, What does it mean for a module to satisfy some assertion? It means that for all other modules M prime, for all configurations that arise from execution of those modules together, the configuration satisfies the assertion. This is an invariant over time, but it applies to the complete module. So these M primes here are the things that allow us to talk about the open world. So we argue that robustness characterization requires a mix of classical and holistic specifications, and we have made the proposal for holistic specifications and applied to examples from contracts and the capabilities literature. And what is stronger? If we have got an abstract data type with classical specifications, we could, of course, imply the holistic specification. Closed means that no function can be added, and all functions will have classical specifications. But why do we need the holistic specifications? Because they are cross-cutting, because they allow us to talk about using functions which have not been, which we don't know about where we are in the open world. And this closed abstract data type is sometimes too strong a requirement. So we have got a Koch model for this. And I would like to use the last couple of minutes left to talk about trust and obeys, which I didn't get to talk about. Here is the paper that we wrote on that. And I remind you that the bank account had several requirements, and the last one, which we call policy 6, says a reported successful deposit can be trusted as much as one trusts the account one is depositing to. And James and I have spent 2 years trying to make sense of what that could mean. But then the answer came when Mark, Tom, and Bill wrote this paper about called Distributed Electronic Rights in JavaScript. And in the paper, they go through 2 examples where they use capabilities. And one of them is about the escrow. So the escrow is about exchanging monies for goods without mutual trust. There is a buyer, the buyer is in blue, and the seller is in green. The buyer gives money to the seller, and the seller gives goods to the buyer. So the buyer has got 2 containers, purses in Mark's terminology, where you can, one is for the money and the other one is for the goods. And the seller has also got 2 purses, one for the money and one for the goods. But they don't trust each other. So how can they make the exchange? They go through an escrow. The escrow does the exchange for them. It offers a function called deal, which has got 4 arguments, these 4 guys here, the purses for the money and the purses for the goods. And it returns a Boolean. And the way that we specify it is if, so the Boolean says, executes, says something about what happened during the deal. So if the Boolean returns false, then we know that the transfer did not happen. And we have also the guarantee that nobody will lose their money or their goods. So the money did not happen. And either the buyer was cheating. So, and this was cheating we expressed through this predicate obeys. So obeys means that this unknown object behaves according to this specification. So either the buyer did not behave according to the specification, and the seller obeyed according to the specification, or the buyer obeyed the specification and the seller did not obey the specification. So one of them cheats. The other, and there are more cases here which I did not want to write because they are not that interesting, or they don't, they are not at the core of what we're discussing. Or the result is true, and then the transfer happened, and both buyer and seller obey the specification, or both the buyer and the seller do not obey the specification. Interestingly, this last case came as a surprise to Mark himself. So even though he had written the code, he had not realized that if the result comes back as true, it can be that both of them were cheating. So if both of them cheat, fine. It's not the escrow's remit to detect it. And how does it work? I'm going to go very briefly through it. We have got the buyer and the seller who don't trust each other. And what we know what we will know at the end of the transaction is that the seller obeys the specification if and only if the buyer obeys the specification. And this can happen through a sequence of transfers. So we first ask the seller to make an escrow purse which they trust. So the seller trusts the escrow money purse. Then we ask the escrow money purse to do the deposit. So that means if the result is true of this, it means that the seller has certified, has vouchers for the buyer's money. Then we do the same in the opposite direction. We ask the buyer to deposit into the escrow. So now if the buyer is valid, then the escrow is valid, and then we do the last bit. So through a sequence of zero money transaction, we have established that the validity of this one holds if and only if the validity of the other one holds. So in summary, what was challenging and what have we done? We needed to think about two-module execution and assertions. I have not gone through that, but it's a kind of visible state semantics. We needed to cater for adaptations for time, because you go from configurations where some variables are in scope and then they're not in scope, but you still need to talk about those variables, dealing with space. Ghost fields, we needed to worry about how to treat cycles. So we wanted to allow cycles in ghost fields. We wanted to allow ghost field functions that might never terminate, but still keep the assertions classical. So then we need to establish language properties. For instance, connectivity begets connectivity. This is one of the standard mantras in the capability literature. We have got a Koch model, and we have got a proof logic for obeys. So we were able to prove the escrow's adherence to the specification. Things that we still are working on is we want logic for proving holistic assertions. At the moment, the way you prove holistic assertions is you argue about all possible executions, so it's pretty cumbersome. Sorry, we have got a proof logic using holistic assertions. So with this one, we could prove, for instance, that in the call of the DOM, the property P of the node, of the particular node, would not be modified. But we also want a proof logic to establish adherence to the holistic assertions. And there are some challenges. And the semantics of obeys, this was an infinite introduction of joy for us, because that also introduced some opportunities for cycles, which we tried to solve with step indexing and back to the drawing board. So these are the things that give us joy now. Thank you.
Thanks a lot, Sophia. That was an amazing talk.
Thank you.
Are there any questions in the audience? Yes. Alex?
Yes, hello. So thank you for the very interesting talk. So I was quite interested in the language for the holistic assertions, because you're using all these concepts such as accesses, changes, the various temporal operations, and so on. And in the talk, it was all given a semantics, very specific semantics in terms of the object-oriented language. And I just wonder to what extent there's an interesting underlying logic of holistic for holistic assertions, maybe based on sort of modalities for these concepts or something like that, that has interest independently of the object-oriented language. And maybe at the end of your talk, you mentioned work on proof systems so maybe that's got something to do with this question too.
I think that for me, the next step would be to consider other languages, like the language I have been working on is class-based. And in the object-oriented family, there are other languages that are object-based, where there are no classes. So to consider that, or even functional languages, if you consider the new versions of JavaScript to be functional. But there is the more underlying question of can this be, and I don't know whether this, so I'm sure that what I said does not answer your question, but is related. I think what would be related to your question, more related, is can these properties be parametric with the underlying programming language? Can we distill what is that we want in the programming language in order to talk about access? I think this is the most fundamental thing. The other modalities about time, there are Kripke semantics, they are known, they are temporal logics, they are not surprising. But we are combining them with the concept of access and with the concept of call. And there is, I think, and also with the concept of identity. The identity, there is the name of something, and what this something is changes with time also. So I don't know. I think this is extremely interesting, and something that I would love to have the opportunity and also the mathematical knowledge to deal with.
Okay, thank you.
Any other question? You can ask questions on the chat box if you don't want to speak up, by the way. And let me remind you that if you do have questions, then you can meet the speaker after the session in Speaker's Corner. In the meantime, well, let me ask one question to you, Sophia. I was wondering about ghost code. I'm perfectly aware that it's pretty subtle to actually introduce ghost code in a specification. In particular, I know about efforts in the Y3 platform where you know, they have put a lot of efforts into being sure, for example, that any ghost code you introduce actually doesn't change the semantics of the ordinary code. But doesn't this problem get a lot worse in the presence of unknown code?
Ah, excellent. Thank you. We don't specify the unknown code, of course. So the ghost code is only is guaranteed not to have any side effects, because the ghost code is not, we're not calling into the full programming language. We are, in the ghost code, we allow reading of field values, conditionals, and calling other ghost code. The reason we want ghost code is because we want to say, we want to be able to talk about properties of data structures without knowing the internal representation of the data structure. For example, I talked about the bank and the account, and we want to talk about the balance of an account. But we don't know how is it kept. It could be that the balance of the account is kept in the object account, or it could be that there is a separate structure, a ledger, and the ledger is a mapping from accounts to their balances. In the first place, the reading of the balance means just read the field. In the second place, it means from the account, go to the bank object, and then go to the ledger and start running through the ledger. So the specification of balance will say, call this ghost function, and this ghost function will be defined differently in the module depending on the representation. But ghost doesn't mean you call a normal function. You call functions from a limited space.
Okay, and are those functions recursive or not?
Yes, they are recursive.
So what happens in the case of non-termination of these ghost functions?
Yes, so this is the subtlety that I did not discuss. If the functions don't terminate, then I'm not going to say it, perhaps I'm not going to say it correctly. If the functions don't terminate, then the assertion that uses the function is going to be false. I'm very sorry, Jean, I'm going to say it wrong, and it's very important, because even though you can negate those assertions, you don't get the logic is classical.
Aha, okay, I see.
We have spent a lot of time creating that. So I can send a little message afterwards, and I will send you a little message afterwards, because at the moment it just doesn't come. But
no problem.
It's a very important part, because exactly that we want to allow the ghost functions to be potentially cyclic.
Okay, thanks.
Thank you.
We have 1 minute left for one last question. So please don't hesitate. It's not your last chance. Okay. So I could probably ask you a last question, but I would really like to give a chance to anybody in the audience. And it's probably too late.
Well,
anyway.
I realize that I think it's not I'm not in the main of the conference. It would be, if I was there, it would be a wonderful opportunity to get some ideas from you how to deal with the cyclic definition of a base.
Well, if you're worrying about the lack of questions from the audience, don't worry. It seems that people are shy on those kinds of conferences.
Yeah, of course. Yeah.
Well, so anyway, it's now 10, so it's time for a break. So you can go to the main room in Gathertown, if you please, or meet the speaker in Speaker's Corner, if Sophia agrees. And,
I will go to the Speaker's Corner. Thank you.
Thank you, Sophia.
Thank you. It was a wonderful opportunity for me. Really, I enjoyed that.
Thanks. Thanks a lot. And then we reconvene at 10:30. Yes, 10:30. See you.
Thank you.